Hello and welcome to this analytical chemistry reviewer, where we will be looking at a few advanced topics and topics which have been a little bit harder to understand maybe, as told to me by the survey of the course. So the topics that we'll cover are the so-called difficult topics, will be Le Chatelier's principle and solubility constant, KSP, both of which are from the equilibrium part of chemistry. The Chatelier's principle typically deals with disturbances in equilibria. Solubility constant deals with how much of a particular solid will dissolve in a solution. Then we'll move on to acids and bases, where we will be identifying strong, weak acids and bases, which is typically a bit of a stumbling block for those starting out in acid-base chemistry. Acid-base properties of salt solutions then after that, and then finally dealing with some calculations such as pH calculations, pKa calculations, buffer solutions, and weak, strong titrations. We, of course, can't cover everything in the course in one session, so these will be the things that we will concentrate on and try to elucidate and make it a little bit easier for everyone. So equilibria, so the equilibrium constant is an important part of an equilibria. So if we consider the reaction here, where we have this N2O4 compound and it is decomposing to give us two NO2s, then we can write an equilibrium constant for this. An equilibrium constant describes the extent of the reaction. So at equilibrium, the rate of the forward reaction, i.e. the decomposition of this into this, is equal to the rate of the reverse reaction, i.e. the decomposition of this into this, i.e. the concentrations seem to be static. However, there are definitely reactions happening. So that means that the two rates can be described like this, where we have they're proportional to the concentration of the two different molecules, and then there is also a rate constant. So then this can be rewritten like this, where the square is, of course, the stoichiometric coefficient of the molecule in the equation. So the ratio constants give a new constant, which is known as the equilibrium constant, which is given here, where K is equal to the rate of the forward reaction constant over the reverse reaction constant, which is equal to the concentration of the product over the concentration of the reactants to the power of their stoichiometric coefficient. So the stoichiometric coefficient here is 1 and here is 2. So this one is going to be to the power of 2. And so that gives us something called the equilibrium constant. And so K is important because it reflects a particular ratio of product concentrations to reactant concentrations for a reaction. So it indicates to us exactly how far a reaction proceeds towards the products. So a large value of K indicates to us that we will have almost complete conversion to a product, whereas a small value of K indicates that we have a large remaining reagent balance. K indicates the extent of the reaction, i.e. how far a reaction proceeds towards a product at a given temperature. So a small value for K indicates the reaction yields little product before reaching equilibrium. This means the reaction favors the reactants. And a large value for K indicates that the reaction reaches equilibrium with very little reactant remaining. The reactant favors the product. So just think about it, because it's a fraction. So the larger the numerator, i.e. the products, the smaller the denominator, i.e. the reactants, meaning that we have more product concentration than we have reactant concentration. But what happens if we're not actually at equilibrium? We have what's called the reaction quotient, which is very similar to K, except that it describes the ratio of concentrations at different times during the reaction at, for example, non-equilibrium times. So for the general reaction given here, where A plus B gives C plus D, where the small letters are the stoichiometric coefficients, we can write the reaction quotient much the same as the equilibrium constant, where Q is equal to the concentration of C to the power of C times the concentration of D to the power of D over the reactants, like so. Q gives the ratio of product concentration to reactant concentrations at any point in the reaction. So it's not just going to be at equilibrium. It could be at the very start of the reaction when we only have reactants and no products, or it could be at it could be like sort of somewhere along the middle as we're reaching equilibrium. So at equilibrium, Q is going to be equal to K. That's an important thing to consider, because no matter what, Q and K are very much related. In fact, K is really just kind of a special case of Q, which is at equilibrium. For a particular system and temperature, the same equilibrium state is attained regardless of starting condition, starting concentrations. Q indicates how close the reaction is to equilibrium and in which direction it must proceed to reach equilibrium. So the reason why it says here temperature is because temperature is important for the equilibrium and it will change the equilibrium constant. Why does it do this? It does this because it changes the rates at which reactions happen. And so it may in fact influence how much of a reactant or product mixture we have. It's not always true that a higher temperature gives more product. Okay, so what happens? So now we've moved on to Le Chatelier's principle because I did a quick review there of equilibria. So Le Chatelier's principle really just sort of describes the disturbances in a chemical equilibrium. So when a chemical system at equilibrium is disturbed, it reattains equilibrium by undergoing a net reaction that reduces the effect of the disturbance. So that means that the system literally moves and reacts in such a way as to go back to the original state. Go back to the original ratio. For example, if we add more reactants to a mixture which is stable at equilibrium, then it will try to reach that same ratio again by producing more products. A system is disturbed when a change in conditions forces it temporarily out of equilibrium. And the system responds to a disturbance by a shift in the equilibrium position. A shift to the left is a net reaction from product to reactant, and a shift to the right is a net reaction from reactant to product. So here we have a system where we have PCl3 reacting with Cl2 to give us PCl5. This is quite a common industrial reaction. And so we'll be seeing what can happen and what can cause shifts to the equilibrium. So say we want a shift to the right, then what we want to do is we want to increase the concentration of either of these two species reactants. And so these reactants will react to produce more product, PCl5. Or we could decrease the concentration of PCl5, and that would force more reactants to react to form the PCl5. So any of these changes causes a shift to the right towards the products. Now conversely, shifts to the left towards reactants will result if we reduce the concentration of either one of these species. It doesn't need to be both, but if it is both, it happens faster. Then PCl5 increase this concentration, we would have an excess of this beyond equilibrium concentrations, and we would see a shift to the left. And so any of these changes causes a shift to the left. So the only substances that appear in the expression for Q can have an effect. So for example, heterogeneous systems with solids and things like that, the solids don't feature in our Q expressions, and as a result, they won't affect the equilibrium position. A change in concentration has no effect on the value of K. So the effect of added chlorine on the PCl3, Cl2, PCl5 system. So if we have this as our equilibrium reaction, our original equilibrium has these concentrations, but say we added suddenly a little bit of chlorine, 0.075. So the new initial concentrations would be this. And so the change here would occur as minus x plus x. And so what would happen is that we would have a reaction where we would reduce the amount of PCl3 and Cl2 and increase the amount of PCl5. So a change in pressure is also going to cause a shift in equilibrium, and all of these shifts are covered by Le Chatelier's principle, where he suggested that systems move to counteract any changes which are exerted on them if they are at equilibrium. So say we have this gas phase reaction where yellow and blue combine to give green, and say it's at equilibrium, then a higher pressure, i.e. a lower volume, is going to cause a shift to form fewer molecules and fewer moles of gas, and that will just try to reduce the pressure. So the fewer gas molecules that you have, the lower the pressure. And conversely, if we increase the pressure, we're going to have a reaction to decompose green into yellow and blue, which will end up creating more moles of gas, which will help to increase the pressure in the system, which will try and counteract that increase in volume. So then the solubility product constant. So this just describes how much of a substance dissolves in solution. And so high solubility constants indicates high solubility. So this is like the equilibrium constant. Just think of it as an equilibrium constant for how much something dissolves in something else. So we have the reactants going to give products. The product in this case is dissolved solid. So the higher this value for KSP, the more solid is going to be dissolved. KSP is formed similarly to K over Q, which is products of reactants. So here, if we have this reaction here, which is silver chloride dissolving to give silver ions and chloride ions, then we can say that the Ksp, the K of the solubility constant, is equal to the concentration of silver ions times the concentration of chloride ions over the silver chloride concentration. However, because silver chloride is a solid, we do not include it in our equilibrium system, or a solubility constant. And so the solubility constant expression ends up becoming the concentration of silver ions times the concentration of chloride ions, much like this. And so solids like silver chloride are emitted as in the equilibrium constant and the reaction quotient. So acids and bases. So moving on to acids and bases, which of course are fairly linked to our equilibria, let's have a look at our analytical chemistry review, where we'll first of all go through a summary of what acids and bases are. So we have several theories of acids and bases that we have encountered in other sessions. And so their use depends on the circumstances. So for example, it started out as Arrhenius and Ostwald, which was the theory of electrolyte dissociation, which was the simplest of the different types. And this Arrhenius theory really just looked at the theory of electrolyte dissociation, which was the simplest. It assumed that everything kind of happened in water, and it was all based on OH minus ions and protons. Then we moved on to this idea of an acid and base reaction giving salt and water. And so that looked at things like the Bronsted-Lowry theory, which was the proton transfer reactions. So that was where we had a base as a proton acceptor and an acid as a proton donor. But by and large, it's still very much connected with the Arrhenius theories. Then in the same year, 1923, Lewis came up with the generalization of previous theories, where he postulated that an acid, in fact, was an electron pair acceptor and a base is an electron pair donor. And this kind of greatly increased the sort of possibilities for what an acid could be. Now, this was largely controversial, and it took 30, maybe 40 years before it sort of gained any significant traction. And it was realized that, in fact, it is a very good way of describing acids and bases. And here, in the case of a Lewis theory, acid and base, neutralization is not really the formation of a salt necessarily. I mean, it does cover the formation of salts, but it encourages the formation of a covalent bond between the acid and the base. And so you can have a whole range of different things happening here, which are not necessarily going to be proton transfers. So saying that, how do we identify what strong and weak acids are? This was a point of concern for some people. So a strong acid dissociates completely into its ions in water, its constituent ions. So for example, say we have HCl, hydrochloric acid. HCl hydrochloric acid is made up of two components, an H plus ion and a Cl minus ion. Those will dissociate completely in water to form the hydronium ion, H3O plus, and the chloride anion. So this is described in general here, where HA plus water gives H3O plus plus A minus. You see, we've written here not an equilibrium arrow, but a straight arrow. And this indicates that really just how significantly dissociated this species is going to be. Almost none of the original HA is going to remain in solution. Almost all of it is going to be completely dissociated. And so a dilute solution of a strong acid will contain no HA molecules at all. A concentrated solution may contain some, but it's still not very much. Now, a weak acid is really anything else, and it dissociates slightly to form ions in water. So it's got an equilibrium now with water, as opposed to a straight up reaction. So HA plus H2O gives H3O plus plus A minus. In a dilute solution of a weak acid, most HA molecules are actually undissociated. So this is a major difference in weak and strong acids. And actually the strong and weak bases follow a similar pattern, where strong bases dissociate completely, weak bases do not. And so Kc for this dissociation has a very small value, usually times 10 to the minus something. Classifying the relative strengths of acids. So strong acids include things like hydrohalic acids. So HCl, HBr, HI, but importantly, not HF. HF is in fact a weak acid. It also includes oxoacids in which the number of oxygen atoms exceeds the number of ionizable protons by 2 or more. So if we look here at nitric acid, sulfuric acid, and perchloric acid, we have a clear difference in the number of protons, ionizable protons, and oxygens. So here we have 1 proton, 3 oxygens. That's a difference of 2. So 3 minus 1 is 2. Here we have 2 protons and 4 oxygens. So 4 minus 2 is also 2. And here we have 1 proton and 4 oxygens. 4 minus 1 is 3. This is a strong acid. Then weak acids are really anything else. If it's not a hydrohalic acid or an oxoacid, it's probably a weak acid. So those include things like HF, which I've already said. It's a weak acid. Acids in which H is not bonded to oxygen or to a halogen. So for example, cyanic acid, oxoacids in which the number of oxygen atoms equals or exceeds the number of ionizable protons by 1. So this is something to be aware of. So here we have HClO and here we have HNO2. These both only exceed the number of ionizable protons by either 0 or 1. So here it's 1 to 1. So that's 0 of a difference, and here it's 2 to 1. That's a difference of 1. So as you can see, it doesn't really fall under the strong acid category that we had up here. And then carboxylic acids, these are organic acids, the ones that contain like carbons and hydrogens and other things. So bases, strong bases include water-soluble compounds containing oxide or hydroxide ions. So these usually are coupled with a group 1 or group 2 metals. So it's like things like lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, things like that. So they have different forms. So Li2O is going to be lithium oxide, LiOH, lithium hydroxide, things like that. Where M is a group 1 metal, then this is the formula for when M is a group 2 metal. And so these are strong bases. And then weak bases are generally just amines, actually. The ones that we come across most commonly are amines. So this is ammonia is an amine. Amines have a nitrogen, which has only got 3 bonds to it. And so it will have a lone pair. Just look up your Lewis structures if you want to prove that to yourself. And so a common structure has an N atom with a lone electron pair. So these are typically the weak bases. So if you see a nitrogen, it only has 3 bonds, then it may well be a weak base. So a special form of the equilibrium constant is the acid dissociation constant, or Ka. So Ha will dissociate in water to form H3O plus A minus. And so we have here a Kc value, which is products of reactants. These products are, of course, the H3O plus, the hydronium ion, and the A minus, the conjugate base. And then that's over HA times H2O. And then we can rearrange this, of course, because the water concentration is so huge compared to the acid components that is typically omitted. And so we multiply through by that concentration. And then Kc times the water concentration becomes equal to Ka, which is equal to this. So remember that the water concentration has not disappeared. It's just been changed to a different constant. So the value of Ka is an indication of acid strength. So a stronger acid means a higher concentration of H3O plus means a larger Ka value. So the larger the Ka value means the more it dissociates. So the more hydronium ions are there, and the more hydronium ions there are, the stronger the acid is going to be. And so a weaker acid has a lower percent dissociation of HA, which gives it a smaller Ka value. So it would have more HA compared to these. So this Ka value would be less than 1, for example. Ka for strong acids. So Ka for HCl is 1.3 times 10 to the 6. What is the fraction of undissociated HCl, we're asked? So we're not given any concentrations, but we can still do this calculation. Usually we're given the concentrations, but not always necessary. So what we do is we simplify this by considering what Ka is, and it is a ratio of products to reactants for the reaction. That means that we're going to have effectively Ka is equal to 1.3 times 10 to the 6 squared over 1. So HCl plus H2O gives us H3O plus Cl minus. So this is the dissociation of this in water. And then the Ka value is given as such, which is products over concentration, products over reactants, the different concentrations of those. This means that there is product to reactant ratio of 1.3 times 10 to the 6 to 1. So we have 1.3 times 10 to the 6 products for every one reactant which remains. So this means we have a huge number of reactants. So how many unreacted HCl's do we have? So the HCl fraction unreacted is going to be 1, which is the one from here, the undissociated, divided by 1.3 times 10 to the minus 6 plus 1, which is the total number of in the system. And so that's going to be 7.7 times 10 to the minus, or a really small number. So basically none of the HCl is going to be in solution as HCl, it's all going to be dissociated. Ka for weak acids, then this is actually where it's more important. So what is the Ka for acetic acid if at equilibrium there's 1 molar acetic acid undissociated and 0.0042 molar acetate? So we have here the reaction where we will see the dissociation of the acetic acid. Then we can form the Ka like so. Then the Ka, fill in the values from the concentration which we had in the question. Then we find out that the Ka value is 1.8 times 10 to the minus 5, just using our calculator basically. So what is the Ka? Acetic acid 0.1 molar if pH is equal to 2.87. So we consider the 0.1 molar acetic acid dissociation reaction, which is the same as before. So H3O or acetic acid dissociates to give acetate plus hydronium in water. So the pH here we're told is already 2.87. So we want to know how much hydronium ion there is in solution. So pH is equal to minus log hydronium ion, which is equal to 2.87 in this case. So we can just rearrange that to get the hydronium ion concentration in terms of the 10 to the minus pH. And so that will be equal to 0.00135 moles per liter. Then we have our Ka expression, which we also saw on the previous slide, and we fill in the values that we have. So we make the assumption, because this is a weak acid, that very little of it actually will be dissociated. And so we will have the concentration, which is dissociated, which is 0.00135 moles. And then we will have that times 0.0135 over 0.1, which will equal 1.8 times 10 to the minus 5. And so that's how we would get the Ka value if we were given such a system. Remember, the assumption that we had here is that very little of the acid will actually dissociate, which holds true in our Ka value. We can check that assumption as we've seen in our previous sessions on weak acids. Then to find the Ka value, Ka is much the same as pH is. So pKa is equal to minus log of the Ka value. So that's going to be equal to minus log times 1.8 times 10 to the minus 5. And then put that into our calculator. We get the value pKa is equal to minus log the Ka value is equal to minus log of that, which is equal to 4.74 as the pKa for acetic acid. So salt solutions, are they going to be acidic, basic, or neutral? So with the identity of the salt determines the acid, base, or neutral behavior in solution. So neutral solutions have cations of strong base and a strong acid anion, which yields a neutral solution. So for example, here we have sodium nitrate. So sodium nitrate is made up of sodium from sodium hydroxide, a strong base, and nitrate, which is from nitric acid, which is a strong acid. Acidic solutions, then, these have a cation of a weak base and a strong acid anion, which yields an acidic solution. So for example, ammonium chloride. So ammonium comes from a weak base, ammonium hydroxide, and chloride comes from a strong acid, HCl. Or acidic solutions can be formed from small, highly charged metal cations and a strong acid anion, yielding an acidic solution, such as iron nitrate. Basic solutions then have weak acid anion, basic cations, which yields a basic solution. So for example, sodium benzoate, which is a weak acid anion and a strong acid cation, or strong base cation. Oh, wait. So let's look at predicting the relative acidity of salt solutions from reactions of the ions with water. So predict whether aqueous solutions of the following are acidic, basic, or neutral. Sodium perchlorate, potassium acetate, iron 2 sulfate. Now I've put brackets here to kind of distinguish the ions, but that wouldn't be present in normal literature or in most exams. So the plan here is to identify cations and anions and to evaluate the ion reactivity with water. So sodium perchlorate has sodium from a strong base, which is sodium hydroxide, while perchlorate anion is the anion from a strong acid, so therefore it's going to be neutral. Potassium acetate has the anion from a weak acid and the cation from a strong base, and so it is going to be basic. And iron 2 sulfate has the cation, or sorry, has a small, highly charged ion, the iron 2 plus, and then the sulfate is from a strong acid, such as sulfuric acid. So the salts of weakly acidic cations and weakly basic anions, if a salt that consists of the cation of a weak base and the anion of a weak acid, the pH of the solution will depend on the relative acid or base strength of the ions. So for example, if we cyanide, ammonium is the cation of a weak base, ammonia, and cyanide is the anion of a weak acid, hydrogen cyanide. So we have this dissociation reaction for, or this equilibrium reaction for ammonium, and we have this for cyanide. So the reaction that proceeds farther to the right determines the pH of the solution. So we need to compare the Ka of ammonia with the Kb of cyanide. Ka of ammonia is equal to Kw over Kb of NH3, which is equal to 1.0 times 10 to the minus 14 over 1.76 times 10 to the minus 5, which is equal to 5.7 times 10 to the minus 10. Kb then of cyanide is going to be equal to Kw over Ka of hydrogen cyanide, which is going to be equal to this, which is equal to 1.6 times 10 to the minus 5. Remember, these are our relationships where Kw is equal to Ka times Kb. Since Kb of cyanide is greater than Ka of ammonium, then cyanide is a stronger base than ammonium is an acid, and so the solution of ammonium cyanide will be basic. So buffers then, acids and bases. So calculating the effect of added hydronium or hydroxide on buffer pH. So calculate the pH first of a buffer solution containing 0.5 moles per liter acetic acid and 0.5 moles per liter sodium acetate. After adding 0.020 moles of solid sodium hydroxide to 1 liter of the buffer solution in A, we want to calculate the pH again. And then do the same thing, but adding acid this time to A. And so we'll start off with the Ka of acetic acid, which is 1.8 times 10 to the minus 5. And we will assume the additions cause a negligible change in volume. So the plan here is, of course, to calculate the initial concentration of the acetic acid and the initial concentration of the acetate from the given information. And from this, we can get the starting pH. For B and C, we assume that the added hydroxide or hydronium reacts completely with the buffer components, and we write a balanced equation in each case, set up a reaction table, and calculate the new hydronium ion concentration. So solution for part A, so we set up our ICE table like so, put in the initial change in equilibrium values, and since K is small, X is small, so we assume that the acetic acid concentration is like given as so, and the acetate concentration is given like this. So both are approximately equal to 0.50 moles per liter. And so X can then be found here as the hydronium ion concentration. And so X is then found to be 1.8 times 10 to the minus 5 moles per liter. And the pH then is equal to 4.74. So check the assumption that less than 5% is dissociated, much less than 5%. It's 3.6 times 10 to the minus 3%. So it's effectively totally undissociated. Then for B, we'll be adding hydroxide. So how much hydroxide are we adding? So we're adding 0.020 moles per liter hydroxide ions. So we set up the reaction table for the stoichiometry where we will react the weak acid with the base. And then we set up the reaction table for the acid dissociation using the new initial concentrations. Then we fill in the values. Since K is small, X is also small. So we assume that the acetic acid concentration is equal to 0.48 minus X, which is approximately equal to 0.48 moles per liter. And the concentration of the acetate then is effectively still the same, 0.52 moles per liter. Fill these into our values to find X. And so X turns out to be 1.7 times 10 to the minus 5 moles per liter. And so the pH is going to be equal to minus log to the base 10, 1 times 1.7 times 10 to the minus 5. And so that will be equal to 4.77. So a very marginally slightly higher pH. And so addition of a small amount of base caused the pH to rise only slightly from 4.74 to 4.77. Then the final part was where we will add acid. We'll add the same molar amount of acid as we did base, this time 0.020 moles per liter acid. So setting up a reaction table for the stoichiometry, again, we react acetate with acid to give us acetic acid plus water. And so these are our initial and change concentrations. And then we will have these equilibrium concentrations and then set up a reaction table for the acid dissociation using the new initial concentrations. We will see, given here, X values are effectively going to be negligible due to the small Ka value. Not a lot is going to dissociate. So since Ka is small, X is small, and so we assume then the acetic acid concentration is this, and the acetate concentration is this, then fill in the values into our X expression, and we find out that the hydronium ion concentration is 2.0 times 10 to the minus 5 moles per liter, and pH is equal to minus log to the base 10 times 2.0 times 10 to the minus 5, which is equal to 4.70, which is, again, a very small change in pH. The addition of a small amount of acid caused the pH to drop only slightly from 4.74 to 4.70, a very, very small amount. And so that was the buffer which enabled that to happen. Okay, then titrations of acids and bases. So we're looking at weak acids and weak base titrations predominantly, or weak acid and strong base titrations, so weak, strong titrations. So what are acid-base titrations? In an acid-base titration, the concentration of an acid or a base is determined by neutralizing the acid or base with a solution of base of known concentration. So we want to know the concentration of acid, so we neutralize that acid with a base of known concentration. The equivalence point of the reaction occurs when the number of moles of hydroxide added equals the number of moles of hydronium originally present, or vice versa. So for example, if we're titrating a base with an acid. And the end point occurs when the indicator changes color. The indicator should be selected so that its color change occurs at a pH close to that of the equivalence point. So strong acid, strong base titrations. So what happens when we add a strong base to a solution of a strong acid? So the titration is the addition of strong base to a solution containing a strong acid. And remember that strong acids and bases dissociate completely in water. And so the overall reaction is therefore H plus OH minus gives H2O. So acid plus base gives water. So the conjugate ions are spectators and do not interfere with the titration. So then the titration of a weak acid with a strong base, the 4 distinct regions of the titration curve include before the base is added, the solution contains just weak acid, HA, and water. And so HA dissociates to give H plus A minus. Between the initial point and the equivalence point, there is a mixture of HA and A minus, which is clearly a buffer. At the equivalence point, HA has been totally converted into A minus, a weak base. The pH is then calculated by considering the base hydrolysis reaction of A minus, because remember the A minus can react with water to give the weak acid again plus OH minus in solution. So at the equivalence point, the excess strong base determines the pH. So the pH will be higher than, for example, in a strong acid, strong base, where the equivalence point is pH 7. So here is the titration curve for a titration of propanoic acid, a weak carboxylic acid, with sodium hydroxide, which is a strong base. So here we have, initially we have only propanoic acid, which only weakly dissociates, but still dissociates enough to reduce the pH. So the initial pH is higher than for the strong acid in solution. And so as the base is added, the base starts to react with the protons which dissociate from the propanoic acid, leaving behind propanoate only in solution. So this propanoate and the presence of the undissociated propanoic acid creates a buffer-like system, which will ultimately cause the pH changes to sort of happen slower. So the curve rises gradually in the buffer region. The weak acid and its conjugate base are both present in solution, and so we have a buffer region formed. Then we eventually have an equivalence point where we have an equal number between propanoate and sodium ions here, but the pH is going to be higher than would normally be seen in, for example, a strong acid, strong base titration. And that is because the presence of those OH minus ions due to the hydrolysis of water by the propanoate. And then finally, beyond the equivalence point, we keep adding strong base, and so we get a higher and higher pH. The pH at the equivalence point is greater than 7 due to the reaction of the conjugate base, in this case, the propanoate, with water. And the pH increases slowly beyond the equivalence point. This is when we have an excess of the strong base. So how do we do these calculations? So calculating the pH during a weak acid strong base titration. So initial pH then is calculated based on the Ka value of the weak acid because there's no base at this point. So it's going to be, of course, hydronium times conjugate base over a undissociated acid, where the hydronium ion concentration is equal to this. Then we have the pH is equal to minus log to the base 10 of the hydronium ion concentration. And so then the equations we used before the equivalence point, the hydronium ion concentration is equal to Ka times HA concentration over A minus concentration, or pH is equal to pKa plus log of the base concentration over the acid concentration. And that's the Henderson-Hasselbalch equation. So pH at the equivalence point then is going to be equal to A minus plus water. Well, this is the equation that we're going to use. This is the one which is going to raise the pH because of this additional OH minus produced. So OH minus concentration is equal to the square root of Kb times A minus concentration, where A minus concentration is equal to the moles of HA initial over the volumes of the acid and base added. And then Kb is equal to Kw over Ka. That's our Kw is equal to Ka times Kb relationship. Then the hydronium ion concentration is going to be approximately equal to this, because what we've done is we've changed Ka with the Ka expression we had on the previous page. And the pH then is going to be equal to the same thing, minus log of the hydronium ion concentration. And then pH beyond the equivalence point is here, where OH minus concentration is equal to the moles of hydroxide ions in excess over the volume of the acid and base. The hydronium ion concentration is going to be equal to Kw over OH minus concentration. And then pH is, of course, equal to the same thing. So let's do one of these calculations. So the problem here is that we want to calculate the pH during the titration of 40 milliliters of 0.1 molar propanoic acid. Propanoic acid was the one we saw in our previous slides. So propanoic acid has a Ka value of 1.3 times 10 to the minus 5. And after adding the following volumes of 0.1 molar sodium hydroxide, we want to know what the pH is going to be. So starting somewhere before the equivalence point, at the equivalence point, and after the equivalence point. How do we know these are, how do I know that? Well, I just know it from experience, but whenever we have the same concentration of the two species, the equivalence point is going to be at the same volume. So if the 40, to get to the equivalence point, we need to add 40 milliliters of 0.1 molar sodium hydroxide because they react 1-to-1. So each propanoic acid produces one proton, each sodium hydroxide produces one hydroxide. The proton and the hydroxide react together to give water, and that's our neutralization reaction. And so we need to have the same number. And so that's going to happen at the same volume, which is going to be 40 milliliters in this case. So the initial pH must be calculated using the Ka value for the weak acid. We then calculate the number of moles of propanoic acid present initially and the number of moles of hydroxide added. Once we know the volume of base required to reach the equivalence point, we can calculate the pH based on the species present in solution. So the solution then for A is hydronium ion concentration is equal to square root of Ka times the concentration initially of propanoic acid. Fill in the values into our calculator, and we get a value of 1.1 times 10 to the minus 3 moles per liter, which gives us a pH of 2.96. Then before we reach the equivalence point, we're in the buffer region, 30 milliliters, 0.1 molar sodium hydroxide has been added. So the initial amount of propanoic acid is given as such, 0.04 liters times 0.1 moles per liter is equal to 4 times 10 to the minus 3 moles of propanoic acid. The amount of sodium hydroxide added is equal to 0.03 liters times 0.1 moles per liter, which is equal to 3.0 times 10 to the minus 3 moles of hydroxide. Each mole of hydroxide reacts to form 1 mole of propanoid. So the concentration, so we produce our ice table like so. So that at equilibrium, we have these values. Fill them in to get the hydronium ion concentration. So the hydronium ion concentration is going to be equal to 4.3 times 10 to the minus 6 moles per liter. And so the pH then is going to be equal to 5.37. So it's increased quite considerably with the addition of that 30 milliliters of 0.1 moles per liter sodium hydroxide. So the 40 milliliters then, that's going to be the equivalence point. So this is the equivalence point because the moles of hydroxide added is equal to 0.004, which is equal to the moles of the acid initially. All the sodium hydroxide added has reacted with the HA to form 0.004 moles of propanoid. Propanoid then concentration has this concentration, which is equal to 0.05 moles per liter. So propanoid is a weak base, so we need to calculate the Kb. where Kb is equal to Kw, which we already know is a constant, over Ka for propanoic acid, which is 1.3. So that gives us a PR minus Kb value of 7.7 times 10 to the minus 10. Then we can find out the hydronium ion concentration like so, which we find out is 1.6 times 10 to the minus 9 moles per liter. So the pH then, by filling in that value, gives us a pH of 8.8. Then 50 milliliters, that's beyond the equivalence point. So the amount of OH minus added is equal to this much. Excess OH minus concentration is equal to OH minus added minus HA initial, which is going to be 0.001 moles. And then the hydroxide concentration is equal to the excess moles of hydroxide over the total volume. So that would be 90 milliliters or 0.09 liters. So that would give us a concentration of 0.01111 moles per liter for the hydroxide ion concentration. Then to find out the hydronium ion concentration, we know the Kw is equal to the concentration of hydronium times the concentration of OH minus. So just rearrange that. And then we get a hydronium ion concentration as 9.0 times 10 to the minus 13 moles per liter. And so the pH then is going to be equal to minus log of that concentration, which is equal to 12.05, a very basic solution. So that is hopefully a reviewer then that will have clarified some of those topics in your mind, and will have refreshed them, and will have made it easier to go forward and have success in analytical chemistry on those topics. Thank you for watching.